So we are going to read an important paper for which
All right.
I would like to request your full attention towards this paper, whose title is, now you'll know why I'm smiling, whose title is Attention is All You Need. It is the paper of the decade, right, in our field. So this paper came out, well, it's not this particular date. It came out in December of 2017. It came out of Google. You notice that Google and a few University of Toronto researchers are involved. All the researchers that you see here, this paper is often referred as Vaswani et al. In research community. Attention is all you need. All of these people who did this breakthrough, they have gone their separate ways. None of them are in Google anymore. They've gone on to found companies and things like that. This title itself merits a bit of explanation. What do you mean by attention is all you need? And a bit of history is called for. It is like this. Let's rewind back to 2017. What was happening is, in 2012 was the so-called AlexNet moment. Deep learning itself used to not be taken seriously. So people like Geoffrey Hinton and Bengio, etc., they were toiling away quietly, while the large part of the computer vision and in machine learning community used to dismiss that work as sort of irrelevant. Not irrelevant, but not as important. It was not central. In fact, that was a time when you wouldn't be able to publish a paper in computer vision journal if you mentioned the word deep neural network or neural network. They thought that is not computer vision. It is unimaginable that it was so, right? And to just short circuit a bit of history of the field, Fei-Fei Li at Stanford created the ImageNet dataset, the largest image dataset at the time, and for which, according to Fei-Fei Li, actually, she said that she was told that she won't get a tenure track position if she works on the ImageNet dataset. Fortunately, she did. That ImageNet dataset was acknowledged. Geoffrey Hinton wanted to have, and researchers wanted to have that their deep learning work recognized. So they convinced the computer vision the powers that be that let's treat ImageNet as the new benchmark. Once they agreed that it is a benchmark, then they brought the next foot forward and they said, oh, by the way, we beat state-of-the-art results on ImageNet, right? And that's how it got a lot of attention. Deep learning had its moment. AlexNet came out. 2 years later, ResNet came out. The generative adversarial networks, the beginning of deepfakes, came out, right? And so as computer vision was galloping ahead fast, concurrently, the hardware thing had begun. People realized that the convolution, the basic architectural unit that you needed to do those computer vision stuff was a massively parallelizable activity. And so you could see that you could repurpose the GPUs, graphic processing units, which were meant for games in those days, for AI computations, for computer vision. And obviously, NVIDIA caught on to that opportunity, and the rest is history. I mean, they literally saw that, okay, oh, our units, our graphic GPUs are being used for AI. We have a new market here. Let's go for it. And they went for it. On the other hand, in the natural language processing world, things weren't going so well. The foundational unit for natural language understanding was something called a recurrent neural network, RNN, whose more mature adaptations were LSTM and GRU. And those are words. I'll just leave it at that. So it was a dogma that if you're doing natural language processing, let's say that translation is a classic way of looking at it. It can translate from English to, let's say, Hebrew or French or Chinese or Mandarin or Tamil, or whatever it is, you would use LSTM or you would use a RNN and things like that. The trouble is, those were sequential machines. Words would go in one at a time. And at the other end, at the decoder end, words would come out one at a time, right? So you couldn't parallelize it. Not only that, they were reaching a saturation point of performance. That is before 2017. And there was a big breakthrough that happened in 2014 whose value was not fully appreciated. In Google, a researcher came out with the concept of attention. So I will explain what attention is shortly. But when attention was discovered, the concept of attention was discovered in neural networks, people tried to treat it as sort of like sugar. A confectionery shop would use sugar. You add sugar to all of your cakes and bakes, and the sales go up. Right? In the same way, you add attention to whatever you're doing, and the performance goes up. So people applied attention to computer vision tasks with CNN, and the results were better. They applied attention to a natural language processing task. They hybridized it with recurrent neural networks, and the translations got a bit better, or the natural language tasks became a bit better. Are we together? So that was the situation in those days. Google, for whom these translations and all of these natural language tasks were paramount, who were really at the heart of all of this, a flurry of activity, they formed this group to say, okay, let's make the really, really powerful architecture that can do these things well. So the history, and this history I heard when NVIDIA gave its keynote this year, they actually, as part of the keynote speech, the CEO of NVIDIA, he gathered all these authors of this paper who had all gone their different ways. He gathered them all for sort of an on-stage conversation, live conversation, in which conversation they actually recounted the history of all of this. So what they said is that they started out by saying, okay, what is the best that we know? For language translation, you can use CNNs. Actually, you can one-dimensional CNNs. You can use RNNs, which is the dogma. Prevailing dogma was you have to use RNN. You would use attention because that seems like the sugar that amplifies the effectiveness or the spice that you add to amplify the effectiveness of all your models. So let's put these three things together. And so they called it, I believe, the cargo net. C for convolution, right? A for attention, right? R for recurrence, and Go, of course, because it's Google, right? So they were going to call it cargo net, or they're playing with the ideas like that. And then in research, one of the things you do is what is called ablation studies. And here I don't think they said it so clearly. So here I'm going into conjecture land. So when you do the ablation study, what it means is if you put many things to build something, you need to know what is the significance of each thing. What happens if you take this out? How much of a performance loss there is in your model, right? These are called ablation studies. So they took CNN out and they realized, oh, performance does not go down. Right? They said, all right. CNNs are not needed. People don't always use CNNs when they are making an architecture for language models. It's great for vision, but not here. Then they said, all right, what else can we take out? Let's take out the RNN, right? And they could take out attention and they could quantify how much they would lose in performance. But when they take RNN out, they did something. It was part of, I suppose, the ablation study. They said, what happens if you take RNN out? And what they found was remarkable. They found that if you took RNN out and CNN out, both of them out, the whole architecture was doing great. In fact, even better. Right? And therefore, the title of this paper, Attention is All You Need to Create a Language Model. Right? That's a real history of this title, which has become so famous. Right? So another question is, what is attention? We'll go a little bit deeper. And why did it work? And why is it so important? One key factor with attention-based network is, and this network that we'll study is, attention, unlike RNN, which takes one token at a time to build it up, Attention actually wants the whole sentence, entire sentence. It is the converse of it. You need to give it the whole sentence because each word needs to pay attention to the other words. Right? And so you can't pass it one word at a time. That wouldn't make sense. Are we together? You have to give it the whole text. Right? And that opens the door for parallelized input. And that obviously means now that the performance bottleneck is gone. What you could do in computer vision, in the same way you could do in natural language processing, you can, in other words, use modern hardware and get acceleration from modern hardware. Right? So that was a huge practical impact of using attention. Needless to say, and so if you read this paper in hindsight, when over the years much has happened, those people, what they really got hooked on is that, hey, you throw away CNN, you throw away RNN, you just use attention, and look, we can do so many things in parallel. And look at the benchmark; it's actually doing better. Right? I don't think at that moment people quite realized what was the complete significance of what they had just built. Right? So with that, we will then step back and ask, before I go into this paper, the word attention, because it was discovered earlier, needs some explaining. What is attention? So the interpretation of attention is not that different from common language, the way we explain attention. So I will sort of deliberately start with a simple analogy. Right? See, you imagine that you're on a hike. You're walking along happily, and as I tend to do early in the morning, dawn is about to happen. The Big Dipper is up in the sky still. Right? This is summer. And as you go, first light of dawn over the hills, I walk next to a creek, a river, and there's sometimes fog on the river, not in the summer, but in the winters. In summer, you don't get that. So you're happily walking along and you're enjoying everything. Your attention is where? In enjoying nature. Suddenly, from the bushes, you hear a growl. What does it do to your attention? Where is it now? Yeah, your eyes are scanning everywhere. Where is that coyote? Where is that mountain lion? There are mountain lions here. Very rarely do you see them, but they are there. Right? And you're in a different mode. So what happened to your what is attention, therefore? Attention is defined by context. You need a context that shapes your attention. In the beginning, when you get out, you have just pulled yourself out of bed, gotten ready, you're in a hiking mood. Your context is to enjoy nature. And so your attention is on natural beauty. But the moment you hear a growl, now your context is survival, isn't it? And by the way, I speak from personal experience. Yeah. No, I never spotted it. So uh, actually, my daughter has spotted it, but I haven't. Hmm? Yeah. It happened when there was a big, this fires happening in the hills. Then I think those mountain lions, because their native areas were distressed, they had all come to Coyote Hills. And so they were there in that neighborhood. I walked a hike in Coyote Hills and next to that, the bay. So attention is defined by context. That is one thing to remember. And because in machine learning, everything is a vector, let's boil it down. You need a context vector, and attention is alignment in some sense to the context vector. Are we together? That's how to think about it. And we will go and think. We will use that. Yeah. Alignment, in the simplest form of alignment you can think of, is what was that mathematical operation we were doing early in the morning? Dot product. Right? So dot product. How aligned you are with a given vector, just take the dot product of yourself with that vector. So whatever vector you're carrying with the context. And you get the level of alignment you are with what is relevant or the context at that moment. So with that basic background and what attention is, let's read this paper. Now, while this paper is about, it says attention is all you need, the more strictly correct definition of attention would be here. something, it's a little bit different from the computer vision attention. It is, so this is too fat. Let me correct it or just add a small modifier for the sake of us learning. Self. So there are different kinds of attention. Attention, self-attention, cross-attention, and so forth. This in particular refers to self-attention, right? Now, with that background, let us read this paper. And it is important that we read this paper carefully and thoroughly. Right? I will read it. The dominant sequence transduction model. Oh, so first I must explain to you what is a sequence transduction model. Let's go into a little bit of a background on that. See, imagine that you are sitting there in United Nations. One person is giving a speech in Tibetan, hypothetically. And your job is to translate it into, let's say, English, Hindi. Right? How many of you know Tibetan? Nobody. Okay. All right. I lived in the mountains. I know a little bit. So Tibetan. So how do you do it? Suppose you are the translator. What would you do? You would hear something in one language. You would process it. You would come up with a mental representation of it. And then you would think, okay, how do I say this in English or whatever language? Or French or whatever is it that you're translating for? Is that how an interpreter would work? So what are the stages? The first is to take in the input, create a mental representation, and then decide how to decode it in another language. Right? So so what happens is input text goes in, which is a set of tokens, words. Remember, we generalize words to tokens. Go in to one part we will call an encoder to come up with a hidden representation, some hidden state, right, that captures the essence of what was said. Are we together? And then you have a decoder that produces, let's say, English, French, etc. And the same translator, for example, may be translating in 3-4 different languages. Once she has understood what was said in Tibetan, she can, of course, translate it into multiple languages as output, right? Theoretically. So in a way, she can have decoder 1, decoder 2, etc., etc. She can decode. But it is only possible if you can create a hidden representation. Now, here is the way the languages go. This hidden representation, strictly, is the language model. It's a model, a representation of what was said, right? That is one strict way of putting it. More broadly, this encoder-decoder sequence architecture. This is a sequence architecture, isn't it? Encoder-decoder sequence. Along with the hidden representation, more generally, people call these are called sequence-to-sequence model. Why is it called sequence-to-sequence model? Because a sequence of tokens go in Tibetan, a sequence of token comes out. They also call sequence-to-sequence model. And in a more general form, these are also called language models. Right? So see, these days we talk about large language models. Large is relative. If you remember the history of big data, what looked like big data in 2001 doesn't look so big anymore today, isn't it? So big or large are adjectives that don't have a quantitative representation. So the really meaningful part of that large language model is a language model. This is a language model. This is what a language model is. It creates a representation that can be used to then forward decode it. Now, decoding could be translation, but decoding could easily be, for example, summarization. Maybe the translator's job is to listen to a lot. For example, what does a journalist do? Goes and chats to a lot of people, and they talk and talk and talk and talk. And after a little while, journalist comes back and says, okay, what did they say? And summarizes it. right? Or the job could be take the language and convert it into poetry. It could do that. Or continue. Suppose I give you a sentence. If I say, I give you one line of poetry or one line of play, or I start a story and I say, continue, go generate from this representation. What do you think the story's continuation should be? So continuation is also decoding, because from the hidden state, you're trying to infer what should come next. Are we together? Actually, strictly speaking, these so-called chats, all of these are continuation machines. Inputs are called prompts. They're called and in a more formal sense, they're the prefixes. And in Google, you often see them use the word suffix. They're suffix generators. Right? They just continue what you wrote in some sense. So all of those are sequence to sequence models, and these are language models. So now we know. And so when you say that the dominant sequence transduction model, are we looking at a transduction? What is a conductance model? Water goes in, water comes out. Transduction means something else. It gets translated to some. There's a transformation in the conductance process, right? In the forward movement process. What comes out is different from what goes in. Does the word now make sense? Right. So obviously, this is written for researchers and by researchers. The dominant sequence transduction models are based on complex recurrent or convolutional networks. We realize that. That was the reality way back in 2017, right? That include an encoder and decoder for obvious reasons. Sequence to sequence models or language models should have that aspect to it. The best performing models also connect the encoder and decoder through the attention mechanism, which is what I said. It was like the pixie dust you would sprinkle on all your neural architectures, attention. And those architectures would start doing better. We propose a new architecture, and here is the crucial word. And in hindsight, it looks like an understatement. We propose a new simple network architecture, which they call the transformer, based solely on attention mechanisms and dispensing with recurrence and convolutions entirely. So guys, just pause and think, how would any person in the field react to that statement? You just broke a fundamental dogma. You needed recurrence. And this thing is saying, oh, you're dispensing with recurrence and convolution entirely. And your first question would be, how is that possible? And that's what this paper is about. They go on to say, experiments on two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. So this is a lot to unpack in this sentence. They are saying that even in the first, you have a conception of an idea. It takes a while to mature it. But they're saying even at the conception stage, it's already proving superior in quality, right? And while you're at it, it's more parallelizable and requires significantly less time to train for obvious reasons, because it's parallelizable, right? And you don't need as much training. Recurrence, actually, in hindsight, you could train for a long time and it was hard to make it work, right? The old style recurrence concepts. Okay, so this is interesting. And I suppose after that, they go on to state results. So I will just say, this is the other big thing, that if you throw away those things, it becomes parallelizable. Right? So notice the emphasis that the claim to fame they are making is that you get superior results and still make it parallelizable and take less time. It was the engineering mechanics of it that they were focusing on at that time. Now they immediately go on to results. Our model achieves 28.4 blue. Blue is a benchmark. And on the WMT English to German translation task, improving over the existing best results, including ensembles by 2 units of blue, by 2 points in blue benchmark, which was good. On the some other English to French translation, our model established a new single model state-of-the-art blue score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training cost of the best models from the literature. So they're saying this simple model, transformer, which needs a mere 8 GPUs, which I'm sure all of you have under your desk. No, I'm kidding. Right? 8 GPU still is nothing compared to the hundreds of GPUs that are needed to train these behemoth models. It's remarkable. We show the transformer. So this is something interesting you notice. That see, while they're talking at a different scale than you and I. Can we train a transformer on our own at home? It turns out it's hard because these things need a lot of GPUs. To authors of this paper, 8 GPU is a mere 8 GPU. To you and me, 8 GPUs is that, can I really afford 8 GPUs? Right? So, and this has been the problem that has stayed thereafter. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. So this is it. And it gives you some detail on who worked on what. But I won't go into the background. Here's the model architecture. See, I said that you need a encoder and a decoder, right? So if they have marked it vertically, whereas I marked it horizontally. So if I were to write the encoder decoder in their way, I would say here it is. Input, decoder. Here's a hidden state that goes in. Does this make sense, guys? Right? So this is the encoder. It's the same thing in our way of looking at it. Now, decoder, by the way, has one quality to it. It is autoregressive, right? Or causal. What does that mean? See, if the only thing I give to the decoder is this hidden state, and I ask it to produce one token, it will produce the token based on the vector, isn't it? But then you ask it to produce again, it will have no choice but to produce the same token all over again, isn't it? So the only way a decoder can produce something different is if the input is different. And so what you do is, of course, suppose you say the cow jumped over the moon. Let's say the French version of it, and you are producing English translation. It produces the word cow. You take the cow, and next time around, not only give it the hidden state, but you take the word cow and pass that also in. Augment the hidden state with cow. And then it says the cow, and then you take both of these and you add that to the hidden state. So whatever gets produced, you feed it back in. You make it the word auto-regressive. Auto-regressive means it learns from it what it just produced or what itself. It is regressing on itself. So that is the nature of the decoder, right? Now, in this, therefore, let me color this part. What is this? Yeah. This part is your encoder. And what is therefore this? Decoder. Now, pay attention to it. If you observe very carefully at the encoder and the decoder, do they look pretty much the same, except for this word masked? Other than that, they look practically identical, isn't it? What does the masked word mean? Masked just means that, see, when you feed it in, suppose you are expecting lots of tokens to come in. You don't know what the future token is. So you just prevent the machine from looking ahead, peeping ahead and saying, oh, what is there? I haven't produced it. Its job is to produce those tokens. Right? So you just hide it, hide those locations. That's all it is. No, nothing very fancy. Now, this paper is encoder decoder. So what is a attention? We'll go back to that. Let's now try to understand that, because this paper is a little bit dense in the sense that it just right away launches into this celebrated equation. So we are going to spend some time unpacking the one equation in this. There's more to it, but this is the equation of this paper. So to how many of you it is dead obvious what it says? It's a little hard to right? So we'll unpack it. See, I told you that suppose I have the cow, jumped over the moon. And you feed that into the machine. Well, you don't just feed that, but for the in the beginning to get an intuitive sense, let's we do that. Let's imagine that you fed this sentence into the machine. So, what are your tokens? Your tokens are the cow jumped over the moon and full stop, isn't it? So the tokens are 1, 2, 3, 4, 6, 7. 7 tokens. What it says, and the whole point of self-attention comes from this. And the reason you use this to create representations for what you say is that each of these words needs to gain its meaning from the context. To illustrate that fact, consider this sentence. They are words, these are called homonyms, like bank. What does the word bank mean? It can have different meanings, right? So if I say to withdraw some money, pocket money, I'm going to the bank, it has one meaning. Then I say, there is a boat at the river bank. It has an entirely different meaning. And then you say, in order to land, the plane banked sharply to the right. Right? Now it has an entirely different meaning. It's a tilt. Right? So the word bank, if you know what it means from the sentence, the words around it, the context around it. Are we together? It is the context that gives full meaning to the word. That was a big realization, actually, that, see, till then, the history of it is there were word vectors. People were trying to represent the meaning of words through word vectors, word embedding vectors. The problem with that is it is not context aware. Right? You can make the best embedding vectors, and people were getting very happy because they found that if you took, like, so just the history of the field was you could do word embeddings in which you could take the king vector, yeah, king vector, and subtract woman from it, right? Sorry, subtract man from it, right? And let's say that minus man takes you here, and you would add woman to it, plus woman. And what you found is you come very close to the queen vector, right? So people began to feel, wow, that's amazing. Word to vec. These are the word embedding vectors. And there was word to vec, there was glove, and so on and so forth, those things. But they reached a plateau of effectiveness. By the way, the word embedding, as you know, it was recently at the NeurIPS given the research breakthrough that stood the test of time. I think it's 2014, where it stood the test of time. It's obviously, it has been a very influential algorithm. Nevertheless, it has limitations. Now, part of the limitations is words pick meaning not just from themselves. Suppose I just remove this word and I just make it the cow hua hua over the moon. Would you be able to give meaning to the word hua hua even though it doesn't exist in your dictionary? Right? You pretty much can guess that it somehow jumped over the moon. Something to do with jumping over the moon, isn't it? Right? So, in other words, quite often the context of a word conveys as much about the word as the word itself. That is the main idea behind using attention in this. What you're saying is, suppose each word is searching for its meaning, for its true meaning. It says that I have some meaning in me, but I can pick up more meaning from the context around me. Are we together? I have a vector, but I can sort of pivot a little bit and gain more meaning from the context around me. How would it do that? So what it will do is each word will then start looking for meaning at the other words. Does that make sense? Yeah. And it may, common sense says that the word cow, for example, it may not pay so much attention to the word the, but it may pay overwhelming attention to the word jumped, right? And the word moon. And it may pay somewhat less attention to the word, for example, the over the, isn't, does that make sense? That it will get more of its meaning from some words than from other words. Common sense, right? And therefore, it turns out that attention is the mathematical vehicle that conveys that fact, that if the entire sentence is the context in some sense, right? How much attention the word cow gives to each of the words, right, uh, has to be different. So let us say that each of the words is given by a vector. There's a vector for there's a value vector for the word cow. There's a value vector for the word jumped. There's a value vector for the word over. There's a value vector for the word the, which is right here, and value vector for the word moon. Let us say these vectors have meaning. In some sense, you want the attention vector of cow to tilt toward the words that give it stronger meaning. Well, of course, itself, because it is a cow, the word cow itself has some meaning in it. You would agree that these words it should be more aligned to, isn't it? So how would you do that? Let's think through it. The mechanism that they used comes from information retrieval. And so I will just pivot away to a simple example of how you think of information retrieval. Remember a hash table? Keywords and looking for it. So in a deterministic world, suppose you're searching for a keyword. Suppose you have a query, Q, right? A Q, so query word, keyword. You look for it and you have keywords, key, value. Suppose you're querying for cow and there is an entry cow, you would pick up the documents that contain cow. That is the very simplified information retrieval way of looking at it. Does that make sense, guys? Now, in the same way, suppose now we translate this to the world of machine learning. In machine learning, the first thing you say, wait. Everything is a vector, right? So your key has to be a vector, your value has to be a vector. Right? So the way sort of, by the way, this is hand-wavy argument. So I apologize for it. It's not as watertight as I am making it sound. So there will be a key cow, where to look. See, what is a hash table? It's a locker room thing, right? Key is literally key to that locker box. So where to find the cow and what is the value of the cow? And let us say that you have a query term, QI, some keyword, and it is trying to determine how much attention to pay to cow, right? Or actually, because I'm using the cow as query, let me use this word as moon here. And so what they posited is that, look, when we create the attention vector for the cow, what it should do is we take all the words that exist. What are the words? The, we, cow, and let's keep going down. The cow jumped over the moon, right? The only thing we need to do is, these are all vectors, and we can add these vectors, right? We can do add of these vectors. Come again? Yeah, of course, because the meaning of the word cow is in the cow word itself also, right? Partly. A word takes meaning from itself and from other words around it. So here it is. So we are looking at the attention, except that we know that you don't want to directly sum all the vectors. Some are more important than others. You need a score. How much value does the cow need to put? A score function. We need a which is a bifunction, score between cow, the word the, plus some sort of a scoring value between cow and cow itself, a score for cow jumped, right? And so on and so forth. Does that make sense? You take a weighted sum. So far we are making sense, right? Now, so all we need to do is have a scoring function. What is the most obvious scoring function we can take between two vectors? Dot product, isn't it? And so you say, all right, now look at this. If you're looking at this term and it wants to pay attention to this, like basically saying, how aligned am I with moon? Aligned means how close I am to that in the vector space to V, to K. And so what you say is, suppose I'm doing Q cow times a dot product with a key of moon, where moon is, like how aligned am I with moon, right? Times the value of moon plus every other thing, plus all the other one, right? I'm giving an example with the moon word. Am I making sense? This is what you would do. And that is all they are saying. This big paper is saying is, this is called the attention score. Score of cow for the word moon. And as you can imagine, it has a certain attention score for every other word, including itself. Does that make sense? Now, let us replace the word cow, because every other word will do that. If I were to replace this word cow with the abstraction ith word, any word, because every word has to pay attention to the other words, right? It is, what is it? It is basically, what's the score function? Score, query I, the query I of the ith word, and then every other word. So let us call the every other word kj times value j. That's how you would do it, isn't it? Oh, and then I better sum it up, because you add up all these weighted additions of over j, right? Because they are j words, 7 words. So you would get the attention vector for the ith, for example, the attention vector for cow. Does that make sense, guys? No. Is it making sense? That is all that this equation is saying, though it's not so obvious, right? So now comes the question. Now, do you begin to see some similarity between what I wrote and this equation number 1? Is beginning to look somewhat similar, isn't it? The only thing is that I have to explain to you now let's map it up. Because this is written in matrix notation, the summation is not so obvious, right? I have deliberately broken it up into pieces. Now, what is the score function? This is it. Right? Now, what is softmax? Let's break it down and understand what is softmax. Softmax is a very lovely trick. Suppose I give you numbers. Right? Throw me numbers, positive and negative. Just say 3, 4 numbers. Come again? Come again? 27. Right? So if you want to do this, if your goal is that, suppose these numbers represent the strength of your belief in something. Suppose, I give you an example. Yeah, or the degree to which you're paying attention, but you want all the attentions to add up to 1. So what can you do? You can just divide it by the total and do it. But then suppose your scores, you insist they should be between 0 and 1. They should be positive between 0 and 1. So between making sure they add up to 1 is easy. Now I also require that any of the numbers shouldn't be negative. They should be positive. So one easy way to make sure that numbers are always positive is just to, well, even easier, exponentiate them. right? Exponentiation of a positive number is a positive number. Exponentiation of a negative number is still a positive number, right? And then what you do is you sum it with, and all of these numbers, if I, what do you get? Each of these numbers will now become a fraction. They will add up to 1, and each number will be between 0 and 1, isn't it? This function is called the softmax function. It is usually all of these large language models' last layer, probability. Why are we so hung up making it between 0 and 1? Because it maps to probability, and the entire machinery of probability theory can be applied to it. Right? That's why we tend to softmax whenever we get a bunch of numbers. So to illustrate this fact, see, look at your LLMs, your large language models. They are next token prediction engines. All they do is they predict the next word. So what does that mean? It means they have a vocabulary of, let's say, 30,000 words, 50,000 words, whatever it is, 100,000 words, a finite vocabulary. Then, as the input goes through the system, imagine 30,000 bulbs lighting up. These are called the logits. From the last layer, 30,000 voltages come out, or strengths come out, logits come out. And you want to convert them into probability. What's the probability of each word being the right next word? This technique will do that for you. That's why you put a softmax there. Are we together? So softmax has a lot of use case. So now, coming back to our situation, if you insist that your score should be between 0 and 1, it's a thing. You just softmaxes. If we just agree that dot product is a good thing to do, you might as well softmax that dot product, because now they won't be negative and they'll be between 0 and 1. And they look like probabilities, a good thing. Right? Also, computationally is better when machines handle small numbers very well. You don't want to risk having big numbers, right? Anything that is small, around 0, machines handle them very well, right? So softmax is a good thing. So now this thing, what I'm saying is, it is q dot k, qi dot qj. This part is okay. Softmax also makes sense. What about the square root of d? Right? This is just a convenience. It's a practical convenience. Don't pay too much significance to it. What it does is computationally is good to have. See, they say it here. While for small values of the two, they just do it. They find that it just leads to better, well-behaved machines, right? So D is the dimensionality of the vector space in which K, Q, V exist. In this original paper, it was 64 dimension. What's the square root of 64? 8. So they're just dividing it by 8. See, remember, it's just a constant. It doesn't matter, right? Because once you softmax it, it'll all get normalized, right? So it is a computational convenience. And now, so this equation, if I were to write it now, in our language, in the language that we understand it, we would say the score is, the score function is of qi kj is equal to what? It is qi kj dot product, right, divided by square root of d, the dimensionality, and the whole thing makes sense to softmax just to normalize it between 0 and 1. Isn't it? Right. Now you may say, now wait a minute, you cheated a bit. There are so many ways I can make sure that a bunch of numbers are between 0 and 1, right? And why use this one, right? There's multiple reasons for it. One of the reasons is it makes the big guy stand out. So think about it this way. Where are those numbers that you guys suggested? This one, right? When you e to the minus 5 is approximately equal to 0, right? E to the 7, when you compare to e to the 15, you realize that e to the 15 is e to the 8 times bigger than e to the 7, right? Which is 1,000 times bigger, right? So that pillar will really stand out. What about e to the 20? It will dwarf everything else, isn't it? Because that will be 8 times 8 times 3, approximately 64, 200 times bigger than even e to the 15, roughly, right? Give or take. So it will really stand out. So what it does is that it makes the big numbers stand out. Right? Which may or may not be a good thing, by the way. In one of the things you do is, suppose you don't like it, that it should get so amplified, you can divide it by what another factor which Geoffrey Hinton called the temperature. You can say, don't amplify it so much. But in this paper, they don't. But I'm giving you the full definition of softmax. Sometimes they do. But all right, I hope you understand this. So what happens is that now let's look at the input very carefully. The cow jumped over the moon. The cow will go into this machine. For every word, there is a K, there's a Q, there's a V. Q, you need to query. K, in a sense, gives you the bearing or the location, as in a hash table kind of thing. And V is the value of that word. By the way, this KQV formalism, while in a hand waving way and using information retrieval, I explained it to you. Some people were a bit not sure if it is the right way. They say, okay, Google does search. So they give away search interpretation to this. This transformer architecture, as people began to realize, is more fundamental than anyone thought. Right? It seems to lead to surprisingly powerful results. It transformed every field. It transformed computer vision. It transformed NLP. It transformed everything. So people have begun to feel that this is more fundamental than anyone thought. And so many other people, like for example, from Anthropic, all of these research groups, Chrysola, etc., they have reinterpreted this transformer without using the KQV formalism. Right? So there are different, more mechanistic interpretations to it. They strongly emphasize residual connections and so forth. We won't go into that. We'll just stick to this. But suffice is to know that there are alternate ways of understanding the transformer that emerged after a few years. So this word, but there is a problem here. If I throw all the words into this, so word first, it has to become, you look up the dictionary, the vocabulary, right? So your vocabulary is, let's say that the first word is aardvark in the dictionary. And let's say that the last word is zephyr, right? Something like that. And so you can give it a number, 1 to whatever, 600, 6,000, 30,000, 30K for the last word, right? And you can keep a special token for unknown, like anything outside the vocabulary, you can give it that index. So what you can do is you can replace each of the word by its ID, right? Which is basically a sequential, its position in the vocabulary. You can do that, right? So this may be 11, let's just say 115, this may be 35. I'm just cooking up numbers. These are not the actual numbers, but you can give it some integer numbers. Then what you can do by a mechanism that is part of it, just assume that we can create what are called word embeddings. A vector embedding, that is the word embedding, a word vector, right? In the traditional sense, you can create. But actually in Transformer, you learn this correct embeddings, but there's a way to convert it into a vector. Once you convert it into a vector, so you have all of this, word vectors. The trouble is, if you feed this into the machine, there will be a problem. Because when you feed it one word at a time, you know which word came before which word, isn't it? Because they are going in the sequence. But if you feed everything all at one go, what about the position? So for example, if I say, no, I did go versus I did not go, you see that. The position of words do make sense. Well, here it's no and not, but you could contrive a sentence where the position really matters, right? So how do you infuse position? Positioning is lost if you send everything in parallel. So what people do is they take it and they put a position vector, P1, P2, because everything is a vector. So you add, you concatenate a position vector to it. Are we together? And it turns out that how do you discover what is the optimal prediction position vector? You can't just give it numbers, because then this vector will become bigger, right? So you have to be smart about creating those vectors, right? There's no reason the last word should be bigger vector than the first word. The position vector should be bigger. So there is a technology, this paper goes into it, which is called the position encoding. It uses some clever trick to do, and subsequently many different tricks came out, right? So I will not be dwelling upon it, because this is one way of doing it. Are we together? Subsequently, other ways were discovered and tried out and so forth. And that is also, it can take us down a rabbit hole. Suffice is to say that what you do is, for every word, you take the word vector plus the position vector to create the embedding vector, the E vector, for each of the word. So you will now have, going into the transformer, the input, the embedding, the E, cow, jumped over the moon. And each of these words, each word, E embedding vector I, will get split into WQ, WK, WB. Sorry, sorry, I take it back. Into Q, K, KI, QI. These vectors, isn't it? So how can you, not only that, the dimensionality of this can be, let's say, n-dimensional vector, n-dim. And here you are deliberately using these things belong to a d-dimensional space. In other words, a QI, KI, VI belong to a d-dimensional space, actually a much smaller space, 64-dimensional space. How can you transform vector from one dimensional space to another dimensional space? Through a matrix transform, right? A simple matrix transform will do it. Are we together, guys? So you have a matrix WQ, WK, WV. So this unit that you create that does it, it is called an attention head. You do more than that. So what happens is that when you do this and then you apply the dot products and out comes the A, this whole machinery, doing all of it together, you call it to be one attention unit. And what they found is, if you use one attention unit and you went ahead and did something, any of your tasks, it was doing it really well. So if one is good, more is better, right? Obviously, the temptation is, okay, one worked. What can we do with more of these, right? And so how can you have more attentions? You realize that some word goes in, AI goes in, to one, it becomes attention, I. So then you can say, now you have attention, other words. Now you can make attention pay attention to attention by feeding this result into another attention unit, another attention unit. So they made it 6 deep in sequence. So this is a sequential way of doing it, isn't it? Then they thought, this really looks good. What else can we do? They said, what if we did this? We created parallel units. Right? And what you do is you treat this together so that collectively they produce the attention I. So you let this produce some attention and you let this produce some attention and you sort of concatenate them. Now, why would you do that? Why would you have two circuits in parallel do things like that? It has to do with the magic of backpropagation and gradient descent. See, think about it this way. You're putting the machine through training. All of these units are talking to you, in a way, learning from it. If all their weights ultimately learned, if the top one and the bottom one, both the attention units have the same weight and doing the same thing, would that be more efficient? Or if both of them were understanding the text in slightly different ways, one was paying attention to the linguistics, another was paying attention to the grammar, semantics, another paying attention to the grammar, another paying attention to some other aspect of the content. That would be more effective, right? because that would be a deeper, richer understanding of the text. Are we together? And what they found is that, therefore, if you have many attention heads through which the same input goes, fans out and goes, and then you keep on joining their thing, what happens is you have a much richer understanding of the language. So one head, many heads. Many head became multi-head. This is that made it multi-head attention. And that is the other part. So you notice that the attention that's coming out from each of the heads, you concatenate them. And while you're at it, now it becomes, when you concatenate them, it becomes a very long vector. Again, you can squish it down by using another matrix transformation. It's just mechanics. You do a linear transformation. And so this is it. Do we understand multi-head attention, guys? And so this paper introduced the concept of MHA, multi-head attention, become an acronym, right? Multi-head attention. And that is what this paper is about. That's all. Why self-attention? Let's see what they're saying in this paper. In this section, we compare various aspects of self-attention to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations to another sequence of equal length, blah, 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 such as a hidden layer, etc. Motivating our use of self-attention, we consider three desiderata. Desiderata means desirable things, properties. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized as measured by the minimum number of sequence operations required. The third is the path length between the long-range dependencies in the network, etc., etc. So I won't go into that. Generally, I leave this for you to read. Let's go straight to the results. By now, I've talked about it, right? The computationally is highly parallelizable and blah, blah, blah. And the network is actually much better, much more straightforward. Look at this. In the blue, which was a big benchmark, compare the performance of transformer in its first, this is now today we call it the classic transformer. The classic transformer right off the bat, what do you say about the results here? Compare it to this column of results, English to a German translation. Do you notice that even in its first version, this idea, this attention transformer is beating the state of the art. The state of the art was achieved by using every known trick under the sun, including ensemble. Means you use a collective wisdom of many, many models, and then, which is computationally brutal, right? Then you put it together, and so it beat them all. English to French, once again, compare it to the state of the art. You see how healthily it beats, right? Everywhere it beats the state of the art. But more interesting, look at the computational, the floating point operations needed to achieve that high level of performance with here. Do you notice that it is 1 or 2 orders of magnitude or 3 orders of magnitude more efficient in computations, right? So massively parallelizable, lower compute, faster. Right? I think at that particular moment, not much remains to be said. Dropout rate is again residual dropouts, etc. So these are minor technical details. When you look at the benchmarks across various things, translations, etc., etc., it generally outperforms everywhere. Then it just shows you what I've been saying, how much attention each word is paying to other words. It's different amounts of attention from the different attention heads. So read this paper, guys. Attention is all you need. I'll leave it as a homework, and I'll put a quiz on this paper to test your self-understanding of this paper. And I'm putting quiz for Bert and the last 2 papers that we covered, sentence and coda, those quizzes I'm about to release, right? So there's a slew of quizzes. Usually I don't release quiz in the first week because a lot of people join in the second week. Right? But you take the quiz. In the beginning, guys, one basic thing about the quizzes, anyway, at this moment I'll stop the recording.